on behalf of the Engineering Science Department and also School of Science and Technology, I would like to thank you all for coming. Also, my thanks to Agilent Technologies for sponsoring this lecture series. Before I introduce our guest speaker for today, let me mention that February the 4th, that's the first Thursday in February next year, I've invited one of the professors of UC Berkeley by the name of Abida Zakir from the Electrical Engineering and Computer Science Department to talk about fast automated photorealistic modeling of large-scale indoor and outdoor environments. For today, our Dr. Shali Saraf is going to talk about recent advances in solid-state laser technology. So, Dr. Shali Saraf is currently an assistant professor in the Engineering Science Department, Sonoma State University. He obtained his Bachelor of Technology in Electrical Engineering from Indian Institute of Technology, New Delhi, and his PhD in Electrical Engineering from Stanford University in 2005. He has several years of industry experience in the Bay Area, Silicon Valley, where he ran an electronic and optical design consulting business. Prior to joining Sonoma State, he was an assistant professor in electrical engineering in the Rochester Institute of Technology in New York. His dissertation work involved building high-power, low-noise, single-mode, quantum noise-limited ND YAG lasers for the Laser Interferometer Gravitational Wave Observatory called LIGO project. LIGO. He is actively involved with the LIGO project, where he currently works on squeezed light generation for subquantum sensitivity. His research interests are in solid-state lasers, nonlinear optics, and high-frequency circuit design. So here is Dr. Saraf.
Thank you, Ali, for your... Oh!
I'm sorry. I hope
One person is enough, one hurt person.
this is the deep one.
You okay?
Yeah, it was hanging, so I'm sorry.
Let me just move
I
this
did
one.
see. Sorry about that, yeah.
Okay.
So it's, no,
Switch it to laptop.
of course, yeah.
Okay, guys, welcome to today's seminar. As you can see, I'm hurting. I sprained my ankle a few days back, so you might see me a little slower than my usual lecturing style. So, pardon me for that. I sprained my ankle. I fell, just to add to the injured list in my house. So, anyways, I'll do my best. So, my talk today is on my favorite topic, which is solid-state lasers, and I want to keep it non-physicsy. This talk, no equations, I believe. A lot of pictures and just looking at fundamentals and putting blocks together. So the picture I have here is one of the lasers I had built at Stanford, and I'll refer to it again. This is called an edged pumped YAG laser, and I will pass this around when I get there. But let's just start off this talk with a little bit of a bang.
Would you like to sit down and speak?
Oh, it's okay. I've taken a lot of Advil, so I'll survive. Okay. So let's start the talk. Can we turn the lights down there a little bit, please, somebody? Let's see what a real big laser can do. Something that's almost working.
Yes, that's clear.
NIF laser. Now, mind you, I didn't make that animation. I was able to get it somehow from one of my contacts there, guys I had worked with at Stanford, a guy called Ed Moses. So he was kind enough to loan me some slides and some of his videos.
What was the fuel they used? Hydrogen?
What'd you say?
They used hydrogen for that fuel?
The fuel is actually a combination of deuterium and tritium. I'm going to talk about that later on. Okay, so having started off, let me continue with the talk. So the outline, I'm already running late. There's going to be a quick primer on lasers. Very, very quick for the students, but I just noticed 2-3 guys, and all of them have been through my photonics classes. We'll go through that very quickly because they should have seen this stuff. Go quickly through the types of lasers commonly used, and we're going to zoom in on solid-state lasers, talk a little bit about slab lasers, the stuff that I worked on a few years back. Then I'll talk to you about rod-based gravity wave lasers that are being used right now in the LIGO project. Then I will again show some NIF stuff, some neat NIF stuff. And if I have time, I'll go to fiber lasers, which are becoming very important, and then we'll try and look at the future a little bit. Okay, laser primer for, I think, Jason, you 3 guys have been through it, so very quickly. Photonic, you've been through the photonics class, so laser primer, this is a 4-level laser. This is the ground state. You excite the atoms from the ground state to some sort of a state out here, okay, up there. And then there's usually a very fast decay to what we call a metastable state. And the atoms sit there for a while, all right? So they have an opportunity to basically perform stimulated emission and come down, and then they decay back to the to the ground state, and the cycle continues. And this is the laser transition. And for the NIF laser, this laser transition is at approximately 1 micron. All right, so that's a good number to remember. It's actually 1.064, but 1 micron is a good number to remember. Okay, so
that's the wavelength?
That's the wavelength, so approximately 1 micron. The laser is a quantum mechanical device. The only way to understand it is through quantum mechanics. Okay, we do try to wing it with classical mechanics, like we talk about this oscillator, which is generally speaking incorrect, but is good enough for the sake of understanding it. So in this little cartoon, we are showing this atom is vibrating with a certain frequency, okay, and this is delta E equal h mu is basically the quantized energy of a photon that will be given out if this atom de-excites itself, or it is going to absorb a photon if the atom is excited. For example, if I have an atom sitting at an excited level and it de-excites itself, all right, what's going to happen is a photon is going to come out. All right, basic quantum mechanics. Generally speaking, if an atom is excited, it's going to stay up there for about 10 nanoseconds. That's a good number to remember. All right, that's called fluorescence. Something is excited, it's going to stick around for about 10 nanoseconds, and then it's going to spontaneously emit a photon. The important thing to remember is that spontaneous emission is an incoherent phenomenon. I could have a whole bunch of atoms spontaneously emitting, but all the photons that they spit out are going to be incoherent, which means there's no phase relationship between them. Okay, and this is important as we go on in this talk. The second thing that can happen is that I have an atom at the ground level. It's sitting quietly at a very low energy level, as an example, and in comes a photon, and lo and behold, the atom is excited, and it's going to get promoted to the excited level. All right, so a photon can be absorbed by an atom. All right, so once this atom is excited, say, with a photon, it is not necessary that it re-emits the photon at the same wavelength. All right, that's some sort of an elastic collision type thing. Generally speaking, what's going to happen is, once he's excited, he's going to kind of decay off to some other level. All right, this is like an energy manifold, and then he's going to drop down in energy, spit out a photon, which is yellow in this particular case, and then it's going to relax back to the ground state. Okay, so the light that's eventually re-emitted after absorption may occur at other colors compared to what it originally absorbed. All right, now we come to the key point about lasers. What Einstein taught us, he said, hey, look, I have an excited atom. All right, this is just a cartoon for excitation. It'll spontaneously emit a photon and go back to the ground state. If it is not moving, that means it's in the ground state. If it is moving, that means it's in an excited state. So that's spontaneous emission that I talked about earlier. The other thing that could happen is that he's sitting quietly in the ground state, a photon comes along, the photon is destroyed, and the atom is excited. All right, so it has been promoted to an excited level. The thing that Einstein taught us, he said, hey, look, if there's an excited atom and a photon comes near it, it is going to stimulate the emission of another photon, which is coherent with the original photon. It is in phase synchronism with the original photon. That's stimulated emission. And you can see this atom is back to its ground state, so it's not moving. Stimulated emission is at the heart of laser operation. Okay? So, imagine I got a photon and I have a medium where I've excited the atoms. I have not told you how I'm going to excite the atoms, just for the sake of argument. Just imagine that I got all these atoms that are excited. They're excited. All right? A photon comes in. A packet of light comes in. What it's going to do is, it's going to pull an atom down from an excited state to its ground state. And lo and behold, I got two photons coming in. And the important point is they are coherent. All right? So this process continues. And what I have is a whole bunch of photons coming out by the process of stimulated emission. And this is at the heart of laser operation. All right? And what laser engineers talk about typically is what is the gain of the medium. All right? Now, the important thing to understand is that the gain is exponential. I had a photon come in. I have 2 photons. I have 4. I have 8, 16. It's an exponential gain. Okay? All right. Now let's put in a couple of mirrors. Okay? The previous thing that I talked about was some sort of an amplifier that I stick in a photon and I got a whole bunch of photons coming out of it. Some sort of a laser amplifier.
And you excite the medium with electricity?
You can do it with electricity. You can do it optically with light. I'll talk about that in a moment. Okay. Ask questions, guys. If Brooks, I know you're a physics guy. Feel free to ask questions. Okay, so what we're going to do now is we got these photons coming out. Then a smart guy said, hey, look, why don't we put a mirror here? Why don't we put a mirror here and turn these photons back in so they can pull some more gain out of the medium? Okay? So once we do that, this whole photonic stream comes back and becomes even larger in intensity. And then I put another mirror here. I bounce all these photons back, and they again regenerate more and more photons. And essentially what we have built is what we call a laser oscillator. Now you must have noticed that this is a 100% reflecting mirror. It means anything that's hitting it, the whole photon stream is going to come back. This has to be less than 100%. Because if it is not, then nothing is going to come out of your laser. It's a useless laser. You can't have 200% reflecting mirrors because you have nothing coming out. So usually one of the mirrors is a little imperfect. Depending on how powerful the laser gain medium is, this might be 95%. I've used mirrors which are 85% reflecting in high gain systems. For a helium neon laser, usually this is about 99.5% reflecting. Okay? So, as soon as the round trip gain becomes greater than the loss, the laser achieves threshold. Okay? And you're going to get a laser beams coming out instantaneously. Okay, so how do I achieve excitation of the atoms? I need some sort of a pumping mechanism, like the question he just asked. In the NIF laser, they use huge flash lamps. You can't imagine the size of these flash lamps to basically optically excite the atoms. Okay? The atoms are optically excited. In a helium neon laser, the kind that you see in the supermarkets, the atoms are electrically excited. All right? So there are different mechanisms by which you can excite the atoms. In a semiconductor diode, again, electricity is the mechanism for causing this inversion. All right? So there are different mechanisms.
On R less than 100%, you said that it reaches a threshold and then it goes through the mirror?
It will go through the mirrors, exactly.
So the mirror is
the loss.
semi-opaque?
It's like a loss. It's like a loss. It's semi-opaque. That's correct. Which means it's going to send back 98% of the light, and only 2% is going to go out. All right? So that's your imperfect mirror. Otherwise, it's just going to build up in intensity, and nothing is going to come out of the laser.
And then, of course, after that, they need to put maybe some lenses.
Oh yeah, I'm not even getting into the optical train after that.
But then you only get 2% or 5% of the energy coming out because
the rest stays inside the cavity. Inside the cavity. Okay? All right. So, types of lasers. Solid-state lasers, they have the lasing material distributed in a solid matrix. For example, YAG, yttrium aluminum garnet, the kind of lasers that I worked with, and these are some of the most powerful lasers in the world, what you do is you dope them with some sort of a rare earth ion, like neodymium, or ytterbium, or erbium. These are the ions which cause the laser action. The rest of it is just a substrate. It's just basically a template. It's just a, what should I call it? Just a holding, like a template to give the material strength and some sort of a crystalline structure. Okay? And the lasing occurs in the neodymium. Neodymium YAG, like I mentioned earlier, it basically emits infrared light at 1064 nanometers. That is the most common wavelength coming out of a neodymium YAG laser. Right? So 1 micron is a good number to remember. Semiconductor lasers, they're universal. In every device nowadays, there'll be a semiconductor laser. As a matter of fact, a good question nowadays would be, what device does not have a semiconductor laser? That would be a better question in a modern context. Laser printers, CD players. I'm sure the iPod has a semiconductor laser somewhere in there. So they're universal. And the pumping is done by electric current. Brooks?
Should that be a micrometers then? Because you said 1 micron instead of nanometers.
Oh, that 1 point is incorrect. It should be 1064, and the decimal should be there.
1,000. Okay.
Thank you. This should be μm, not nm.
Okay.
All right. In the olden days, what people did, if they wanted a lot of power coming out of the lasers, they used dyes, organic dyes, such as the most common ones, rhodamine 6G. You can still buy these. All right. Some smart guy said, "Hey, look, we want to make a laser weapon. Let's put these huge dye lasers on aircrafts. It'll work. The only problem is these dyes are highly corrosive. If you have a slight leakage of the dye, that's the end of your aircraft. All right? They work, but they're very, very dangerous to handle. Highly corrosive. There are problems with containment, leakage. So if you want to stay away from dye lasers, that's probably a bright idea. If you can get your energy from some other medium. All right? And finally, gas lasers, helium neon lasers. Every supermarket has them. Argon ions, they laze in the visible, UV, and also in the green. You can get green light coming out of argon ion lasers. CO2 lasers laze at 10 microns, and they're used for cutting hard materials. So these are gas lasers. But the focus of our talk is going to be solid-state lasers. All right, so laser amplifiers. Let's just jump right into laser amplifiers. A laser amplifier, basically what it does is, it takes a good signal from a very low power oscillator. Mind you, it is easy to build a low power oscillator rather than a high power oscillator. Right? You can control the properties, the beam quality of an oscillator, which is about less than a watt. It has been done, and the kind of oscillator I'm showing you is what they call a non-planar ring oscillator. And I don't expect anybody to understand the details of that. This is the best oscillator that has been invented, and it came out of my lab at Stanford. My advisor is the original inventor of this. Okay? What you do is, this has a very high degree of coherence and very good beam quality, and then what you do is you try to put it in an amplifier and basically amplify, increase the power of the signal without losing its original good properties of high beam quality and coherence. All right? So this system, the acronym is MOPA. If you work in the laser field, people talk about MOPAs, till the cows come home. But MOPA stands for Master Oscillator, a good guy, good little guy, followed by a big honker, power amplifier, whose only job is to amplify the good signal coming in. All right? So this is one way you could build a laser amplifier. But you know what? This is not a very bright way of building it. Turns out, in order to extract the energy from a power amplifier, the signal that you're going to drive it with should also be of a significant power level. Otherwise, what's going to happen is you're going to leave most of the gain behind in the laser material. As an example, in this first part of the slide, I came in with 300 milliwatts, and the best I could get out of it was 45 watts. All right? Then I said, you know what? I'm not really using this gain material well. So what I'm going to do is I'm going to put a preamplifier here to get it up to a reasonable amount of power. In this case, it's 25 watts. Now I can really pull all the power out of this power amplifier. It's like money. Okay? If you put a little bit of money, you're going to make a little bit more money. If you put in a lot of money, you're going to make a lot more money. I mean, this has an equivalence. All right? So, in laser amplifiers, what you want to do is you want to saturate the amplifier. The technical word is saturating the amplifier. In the first case, I'm really not saturating the amplifier. I'm leaving a lot of the gain behind because the incoming signal is not strong enough to pull all the excited atoms down for amplification. In the second case, what's happening is I have built up the power of this pristine oscillator to a significant level, 25 watts. Just from experience, that's a good amount of power. Now I'm really able to saturate the power amplifier and get all 100 watts out of it. All right, so this is the concept of saturation. And turns out, and this is part of my thesis work, if you saturate an amplifier, the noise is much less rather than the noise coming out of an unsaturated amplifier. All right, so this was the bulk of my thesis work.
So the noise is going to reduce when you go to saturation.
Yes.
Right?
What happens is that if you do not pull these atoms down with your incoming signal, they will relax down through the process of spontaneous emission. And that's all noise. You do not want that in a high-quality laser system. So what you want to do is you want to saturate the hell out of it so that you have minimal spontaneous emission. Everything is coherent and stimulated. Okay? All right. So this is just to summarize it. To create high intensities on a target, this is my target, we need a power amplifier. And to drive a power amplifier efficiently, which means we want to saturate the gain, we need to drive it with sufficient power, usually provided by preamplifier, where the gain is only partially saturated. Okay, so important laser amplifier systems. The NIF system that I showed right at the beginning of the lecture. Flash lamp pumped neodymium glass slabs. Turns out, for NIF, the power requirements are so intense, neodymium YAG would not have worked because it's not easy to make these huge slabs of neodymium YAG. Instead, for the NIF system, they use neodymium glass slabs. All right, so you've got these huge slabs of glass, and the lasing ion is neodymium. And you get 1.8 megajoules in one pulse, and the pulse is approximately 20 nanoseconds, and there are 192 beam lines that are working in synchronism, and they finally hit the target. The second important laser systems, when I say laser amplifier system, I'm talking about really high power, is the NGST, where NGST stands for Northrop Grumman Space Technologies, and they're down in El Segundo in Southern California. All right? A lot of their work was very similar to the work that I did for my thesis. They use what are called end-pump slabs. Of course, they're NGST, not a little university, and they're able to use a large number of these slabs, and they're aiming for about 100 kilowatt laser. The last I talked to them, they had about 20 kilowatts coming out of a single slab. All right, so then what they do is they've got all these amplifiers, then they beam combine them to get about 100 kilowatts in the far field. And the hope is to get a megawatt. That's what the US military wants. All right, they want a megawatt of power coming out of these lasers, so they can put them on aircrafts and do bad things. But then the bad guys could always take a big mirror and shine it right back at the aircraft who is trying to take them out. So it'll be interesting how this whole thing evolves.
In fact, I think that was one of the ideas that came up during Reagan administration, that they wanted to have laser beam just hit the rockets which may come from other countries.
Yeah, that's part of the Star Wars, one of the elements of that.
Was, I mean, the project was killed. I mean, it's not there anymore.
Yeah. And the third system, which is important, is Raytheon. Again, these guys are down in Southern California. I've visited with both these companies. What they're doing is they're doing something very similar, but instead of pumping the ends of the slab, they're pumping the edges of the slab, which has some advantages in terms of scalability. Again, they're using YAG slabs, but they're doped with ytterbium. And just as a point, ytterbium in YAG lasers at 1032 nanometers, and neodymium in YAG lasers at 1064 nanometers, just a difference of 32 nanometers. But they're both 1 micron infrared lasers.
The NGST was by Hughes or what?
It was huge, then it was TRW, and then NGST bought their space division. And they're doing very well, by the way. So, okay, so that's laser amplifier. So this is a NIF amplifier I showed you guys earlier, and we're going to talk about it in more detail. But I wanted to show in the slide is the enormous size of the slabs, the neodymium doped glass slabs. 3.4 times 46 times 81 centimeters, and they weigh 42 kilograms each. Okay, and how many of these do we have? 3,072 for the 192 beam lines that run in the NIF laser. It's incredible. If any of you gets an opportunity to go to NIF, it is really an experience. I visited there a couple of times when I was a graduate student. It's just an experience of a lifetime to see working hardware at this level.
So there should be an array of all of these.
192 of these.
Yeah, and then now the array, I mean, it's going to take a huge area. Then,
It is. It's the size of a football field. Okay, I'll show you some slides as the talk evolves. Anyways, this is this huge amplifier.
Sherry, does wavelength have any role to play in these high power lasers?
What? Jagan is asking a good question. He said, any relationship with wavelength? Turns out the materials with the highest gain are typically these YAG-based material, and most of them laser about 1 micron. Okay? So people have mastered the art of constructing these big old slabs where the lasing ion is neodymium, and neodymium has a very high gain. So that's why everybody who wants to build a high power laser will usually go for around 1 micron. So this whole system runs at 1 micron, and what they do at the end is the frequency triple it. The 1 micron becomes blue light, and that's when they hit the target. Right? We'll show you all this stuff momentarily. And you can see some guy was very smart. He put a debris shield here. Okay, not a good idea looking into this stuff.
Just this diagram on the top is really good. Let's see now. Can you go through that? Please?
Yeah, it's basically a bunch of amplifiers. Okay, so what you do is when you have an amplifier, and you put a laser beam through it, okay, it's going to increase in intensity. But turns out there is still a lot of gain left behind it. It's not fully saturated. So generally speaking, what we will do is we'll send this guy back in through the amplifier. Okay, so that's what those mirrors are. Those mirrors are basically sending the signal back through the slabs a few times so that you completely saturate it. And then you kick it out. And then again you amplify it. And these are called spatial filters. Turns out, after amplification, a beam that would normally look like this picks up some crap. It might look something like this. All right? So what you do is you put a lens and focus this beam down. All right? And then what you do is you put a pinhole here. So what the pinhole is going to do is going to scrape off all this crap and just leave you with the fundamental mode. And then you amplify it again. So that's the concept behind these spatial filters. Now mind you, this is a high power system. When you focus it down, you better do it in vacuum. Otherwise your air is going to ionize. All right? So these spatial filters are in vacuum. Because the electric field is so intense at the focus, you're going to have a catastrophic event.
Yeah, because even if it touches the material there, it will...
Not just the material, the air. Air is going to ionize.
Yeah, even the material around it, I mean,
there will be electric field here also.
Yeah.
All right? If it ionizes, you could basically damage a pinhole and have a fire. So just something to keep at the back of your mind. All right? And along with the slabs, you got a whole bunch of mirrors, polarizers, grating, shields. Question?
What are the doubler crystal and the tripler crystal?
Yeah, that's basically you want to get to the green, to the blue.
So you're doubling the frequency?
Doubling in frequency.
To get higher energy?
To get a more energetic photon, which is going to hit your target.
And the coherence of the beam remains?
The coherence of the beam remains.
The slab, what does the slab do exactly?
This is the amplifier. This is the gain material, which is going to be excited, like your original question, with big flash lamps.
Okay. On the side.
On the side. Or we call it face pumping. You're going to excite the face and the beam comes in like this.
Now the slabs in that diagram.
Uh-huh. Oh, those are all in the amplifiers. Right, these are the slabs.
Sure, right, exactly.
This is just a cardinal. They couldn't possibly show the whole system. It is so complicated. Yeah. They're just trying to make it a little readable. Okay? All right. So guys, real quickly, I'm just going to... There are two ways you can build a laser. One way is, like I indicated earlier, you have a low power oscillator, and then you amplify it and amplify it. This is the MOPA system. The second thing you could do is you could build a big honking oscillator. Nothing is preventing you from building a 200 watt oscillator. All right? As a matter of fact, in the gravity wave project that I work on, the Germans have built a 200 watt oscillator. I built a 200 watt MOPA system. We had a competition going on. And at the end, even though my system was superior, they won out because the German government gave them about $2 million to build the laser. So LIGO said, hey, Shelly, thank you very much. We'll give you a PhD, but they're going to build the laser. So I'm going to talk about this laser. It's a 200-watt laser. Okay. Beyond 200 watts, it becomes extremely difficult to control an oscillator. You do not want to go beyond that. I don't know how only the Germans could build a 200-watt oscillator. Okay.
So why is that?
Say that again.
Why is that? Why is the 200 watts the limit?
Because after that, the oscillator, slightest thermal perturbations,
Okay.
slightest geometrical perturbations throws the thing off.
Right.
You will get power out of it, but you will get a very crummy mode coming out of it. It becomes really difficult. I mean, I have experience with that.
Okay.
All right. This is much easier.
Is it possible to have a mirror that can switch off and on so quickly within a wavelength, maybe, so you could actually use 90 instead of using 5% that leaks through, use 95%?
Okay, you're saying that if there's a pulse that's going back. I mean,
Yeah.
conceptually it can be done, but remember, when we're talking about terahertz frequencies, you're talking about femtoseconds or less than femtoseconds for something to move. And it's physically not really, we don't have the means of doing that. Conceptually, yes, you could do that.
Why would someone then go to build injection lock oscillator if it has this kind of instability? Is it simple?
Good question. This is one of the reasons. Noise. An oscillator, from the noise point of view, is better than a MOPA system. Okay, because what you've done is an oscillator, because the photons are going back and forth, you've saturated the thing completely. While in an amplifier, there are always some atoms which are sitting there and spontaneously emitting into your lasing load. So that is the key advantage of a bigger oscillator.
Yeah, would the noise be also due to the heat generated in the area? Because there will be some heat. I mean, in cavity, there will be some heat generated. It's going to affect the whole system.
Very good question. So what you do is, that's the reason you use what's called an injection locked oscillator. The big oscillator, you don't want him running on his own. What you have is another oscillator which has much lower power, and he's basically seeding the big oscillator and forcing the big oscillator to run at the frequency of the master oscillator. Okay? So what you're doing is, the thing that you can control is injecting into the big guy who you want, but who you cannot control that well by using the concept of injection locking. Injection locking is used in electronics all the time. It's used in optics, in lasers, very commonly.
What type of locking range usually accurates?
Good question. He's asking what is the locking range. It depends upon the relative powers of the master and the slave. Okay, so as your slave gets higher in power, you can move away as far as the frequencies are concerned.
So slab is somehow giving you some sort of Q, like normal electronics oscillator. We talk about like low Q or high Q. Is that the same kind of thing happening here by changing the slab?
By changing the slab?
I mean, are you changing the Q of the oscillator?
No, what we're doing is we're basically saying, hey, look, I've got this gain curve, or you can call it the gain bandwidth curve of the big guy.
Right.
He wants to oscillate out here, but he can move all over the place because it's not stable. So what you do is you say, you know what? I'm going to put in a very strong signal right here. And what happens is it quenches this oscillation, and the big guy starts oscillating at this frequency. Okay, that's the concept of injection locking. Very, very powerful concept.
Some of that also depends on the Q.
Depends on the Q of the cavity, that's correct, and also the relative powers. Okay, you can't have a little guy try to injection lock this monster. So usually what you would do is you would have an intermediate stage, and I'll talk about that in a little bit. All right, is everybody clear about this oscillators with amplifiers? Okay, YAG. I'm not going to go into the details of this. The only thing that I want to point out to you guys is when you optically excite neodymium YAG, we usually pump it at 808 nanometers. Okay? 808 nanometers, and it lasers at 1064. Mind you, 808 is a more energetic photon than 1064. Right? Shorter the wavelength, more energetic the photon. So what happens to the remaining energy? I put in an 808 photon, and out comes a 1064 nanometer photon. What happens to the rest of the energy? It goes in heat. Okay? And that's the number right here, 76% photon efficiency. So for one photon at 808, I get a photon at 1064, the rest is lost as heat. And that is the main thing that laser engineers deal with, is how to get this heat out of these systems. It becomes more of a thermal engineering problem. All right? The physics is well understood. So what people are doing are basically handling the thermal load of the lasers.
And the cooling is done by
It's done by
water.
water. Okay? One method is by water. All right? So YAG has a good advantage. It has high fracture strength, high quality crystals are available. So that's why this is, generally speaking, the material of choice. And now what people are doing is, instead of neodymium, they're using ytterbium as the host material, as a lasing material. All right? And the only difference is, instead of 1064, ytterbium lasers at 1032 nanometers.
You mean yttrium?
Ytterbium.
Yttrium.
Not yttrium, ytterbium,
Okay.
the rare earth material,
Got it.
rare earth ion. Okay, so now, in the abstract, I had mentioned that I want to talk about different kinds of medium. The two most popular mediums, or configuration, or geometries for YAG lasers are rods or slabs. All right, rods were used for a long time, but turns out, without getting into the physics of it, you get a very strong thermal lens in rods because of the heat. Okay, and it's astigmatic, which means if you were expecting a round beam, you're going to get an elliptical beam. All right, and also, as the rod gets hotter and hotter, you get what's called depolarization. Right? So something that should have been coming out vertically polarized, the polarization starts turning. All right, and if there's a polarizer sitting out here, you're going to see a loss of power. Right? That's a big problem with rod lasers. Okay, now General Electric came out. These are the days when big companies used to have these outstanding labs like General Electric, Hughes. These are premier research labs, and they were doing research which was comparable to the best universities before big Harvard-educated MBA CEOs came and dismantled them because they were looking for a profit in 3 months. All right? So the zigzag slab was originally developed at General Electric labs. All right? So the idea is, hey, look, I've got all these thermal effects inside the gain medium. Why not zigzag? With the result, I'm going to average out all the effects. And it works. All right? And what you do here is you have total internal reflection occurring here. You just zigzag your way through the medium. And these are the kind of slabs that I worked on, called zigzag slabs. So what it does is, it minimizes what I called earlier the depolarization, where the polarization turns and you have a loss of power. It minimizes that. Okay? The only problem with slabs is, because you can see that it has got a nice rectangular geometry, sometimes what happens is that if the atoms are excited here, you can have a lasing medium, a lasing path, which goes like this. You have an oscillator occurring in the transverse direction, a serious problem. All right, so we use all kinds of techniques to minimize this parasitic loss.
Also, would they?
Because a laser wants to see shining surfaces. So the moment there are shining surfaces available and a closed path available, he's going to just right away take that path, ignoring that the fact that, hey, my signal is coming in the longitudinal direction.
Now, would there be more heat generated in the whole slab now when you have zigzag thing?
The heat generation is only a function of that quantum defect I talked about earlier.
Yeah.
The heat generated, whether I have a rod or a slab, it only depends upon the difference in energy between the pump photon and the lasing photon. Right, so that's not an issue.
No, but I'm talking about the volume, because the volume now is smaller.
Not necessarily. You can have tiny slabs. As a matter of fact, what I will do now is I'll pass around a zigzag slab that I had designed during my graduate days. This is the slab. All right, and I had 200 watts coming out of the end of the slab. All right. You can touch it now. I doubt I'll do this experiment again. Okay, so I just have a couple of slides on slabs. This is another way that you could have a zigzag slab is you're going to excite it with light which is coming in the edges, which is this system. I don't know how well you guys can see this. Underneath the copper plates is an actual slab. There's a neodymium YAG slab here. The signal comes in from here, zigzags, and comes out of here. But I got to optically excite this YAG. So what I had done was I had put in fibers going to laser diodes. The laser diodes are out here, and they were at 808 nanometers. With fibers, I had about 12 fibers on either side, pumping and exciting the YAG. So that's the pump I'm talking about here. Okay? The pump is here, and this is the picture of this whole system when it was operational. By the way, I didn't steal this. I took it by permission. Many people asked me this question. How do you start walking away with university stuff? This was a spare one, so I was able to take it out. All right. So from this slab, we got about 120 or 130 watts coming out of this slab. Right? Not that slab, the slab that's in there. Okay. Now this is the other geometry I talked about. The slab that was in Jacob's hand a moment back. This is what we do is we pump it with light from the ends, not the sides. And what happens is by total internal reflection, the pump light is guided through the slab. Okay? And similarly, we zigzag the signal through it. All right? But what is not shown on this diagram is what we call multi-pass. In multi-pass, what I had done was, once the signal goes in and zigzags, all right, there's a whole bunch of gain still left behind in the slab. So what I did was, I turned it around and sent it back in and double passed this. So now I was really able to extract a whole bunch more gain than I would if I had just done a single pass. All right, so this is one of the things that you must have seen in that NIF slide, the laser thing going back. All right, so that's exactly what it is. It's a double pass. All right, so you're able to extract more energy out of the slab.
Would there be any interference at all?
In terms of what?
When you turn the light back again through the same slab? No interference?
Interference in what context?
For the light, because basically now they are going to the whole light is going to excite the atoms of the slab and so forth, and then it just goes back and forth. So and then if they hit the same spot or whatever.
If they hit the same spot and there's not enough gain there, it doesn't matter. It will just not pick up any gain from that spot. See what I mean?
Traveling in two different directions.
You're traveling in two different directions. So if I already got the gain out of this, if the second guy who's coming back lands up in the same region, he says, sorry, I have no more gain for you, man. Go ahead and look for it somewhere else. That's just one way of looking at it. The concept of double pass. All right?
What's this slab made out of? It's glass
YAG.
with a coating?
It's YAG.
Oh, yes, yeah, sorry.
Okay? So, NGST, this is their basic building block for their 1 megawatt laser. All right? Obviously, they're a big company and they have bigger slabs, they have a lot more money, but conceptually, they're doing the same thing that I did. All right? This is the kilowatt laser building block.
What's TMOO?
TMOO, you can have a laser who's giving out energy in many ways. It could look like this. It could also look like this. All right? The highest brightness laser is what we call a TEM00, which is basically, in simple words, a round beam with no crut around it. All right? You could also have a laser beam which looks like this. These are called higher order Gaussian modes. All right? But as a laser engineer, you're striving for this kind of a beam. Right? Highest brightness. Okay. All right, so what I want to do now is, I think I'm running short of time, I'm going to skip the LIGO and go to the NIF laser. All right, so I've given you an idea of how slabs work for extracting gain. Now what I want to show you guys is what's happening at the NIF facility. All right, 1985, they were building a laser called the NOVA laser. All right, it was a kilojoule caliber laser at Livermore. And now, in 2009, we have the NIF laser, the National Ignition Facility laser. All right? This is just stuff from Ed Moses. He's trying to impress people, so I'm going to skip this. Has anybody been to Livermore?
We have passed through that.
You passed through it? Okay. This is a pretty massive facility out there. Right here is your NIF facility. Okay. Livermore also incidentally happens to have one of the biggest Hindu temples in the North Bay area. So a lot of people go there to the temple, and I tell them, you know what, why don't you go by the NIF facility also and see some good stuff. Okay, NIF is now operational. Okay, this is the largest scientific project completed by the Department of Energy. All right, it is not run by the military, it's done by the Department of Energy. NIF concentrates all 192 laser beam energies in a football stadium-sized facility into a millimeter cube. Right? All that energy is finally concentrated. And these are some of the temperatures and the pressures that will be achieved once we are close to fusion. Right? Just to give you an idea, the temperatures, 3.5 times 10 to the power 6 K. You're basically trying to fuse things together, so you need enormous temperatures and enormous pressures.
So this basically used for fusion, right?
For fusion, yes. Okay.
Is that the order of the temperature of the sun? Like
It is. That was the initial video which was shown before you came in.
Right.
Basically, the fusion that's occurring on the sun, we're trying to recreate it in the laboratory.
Okay.
All right.
The interior.
Huh?
The interior.
The interior of the sun, yes. That's where all the fusion occurs. Hydrogen is being fused to make helium and give out energy. Okay, these 192 beams, their frequency tripled. Okay, the work is done in indium glass, but their frequency tripled in a crystal called LBO. All right, I'm not going to go to those details. 1.8 megajoules. The peak power is 500 terawatts. Remember, 1.8 megajoules in a 20 nanosecond pulse means the peak energy is enormous. All right, we're not talking about average power, we're talking about peak power. And the wavelength after frequency tripling is 351 nanometers. All right, it's kind of blue. All right. 192 beams were operational last year, September 24, 2008, and they really have built them in 4 clusters. Right? 192 divided by 4, that's 48 beams in each cluster. All right? So 4.2 megajoule, 1 omega means 1 micron, the 1064, the wavelength at which all the amplification is occurring. And then when you do the frequency tripling, it's called 3 omega. This is the target chamber. All right? All these holes that you have in there, some of them are for sending the laser beams in, but most of them are for diagnostic purposes. There are all kinds of sensors looking at X-rays, neutron counts, gamma ray cameras, stuff I don't know about. All the principal investigators who go there to study plasma physics, they have their own sensors and instruments which are just all over the place. Right? So 1999 was the dedication ceremony, and it was operationally qualified to 1 megajoule. 1 megajoule, mind you, 3 omega, which means at the blue frequency. 3 omega is a triple frequency. Right? 1.1 megajoules. And that's telling you that the process of conversion from 1 micron to 353 nanometers is a pretty efficient process. All right? These nonlinear crystals are highly efficient. This is Arnold doing it this year, May 29th, inaugurating it. All right? He took all our money and gave it to NIF. So, right now, NIF is operational, conducting experiments and acquiring great data. And this is the target. Right here is the target. Right? This is the chamber, the ignition chamber. And this lady is looking at the target. Okay? And this is the fusion target. Right? And I'll show you a film about it momentarily. Silicon arms, there are a bunch of heaters in it. A lot of the principal investigators are also chilling the target, trying to study what happens when you hit it with a laser beam and it's cryogenic. These are the beam lines. Each of these tubes carries a laser beam. All right? So essentially what's happening in NIF is that you are taking these isotopes of hydrogen. All right? Hydrogen has a proton and an electron. Deuterium is heavy hydrogen. It contains 1 neutron. All right? Tritium contains 2 neutrons. I'm sure Brooks has taken his modern physics class. They must have taught you this stuff. So what you're doing in fusion is you're combining these 2 guys, and out comes helium along with a bunch of energy in the form of neutrons. So let me see if I can go and show you. Is this the video? Okay. Let's see this video also. Again, this is courtesy of NIF. And what did I do here now?
You can go to view and then full screen.
What do I need to do?
Excellent.
Okay. Let's see. All right, guys. So the question that we should be asking is, what in the world is going on here? Did anybody have any ideas? There is a laser beam coming in, right? What's going on here?
Is this your double or triplet?
What's happening here is somebody has to feed it a constant stream of pellets. This is futuristic. This hasn't happened yet. All right? If you've done ignition on 1 pellet, you got X number of, say, watts of power, then what are you going to do? You're going to sit around? The thing is useless. Yeah. If it's really going to be a source of energy, you're going to have some mechanism which is refreshing the little pellet there. So what you're seeing here is the pellet gun, not designed yet. This is all conceptual, the artist's work, which is constantly shooting in a stream of pellets, these deuterium pellets I talked about, and getting ignited and continuously making power. You can imagine this is some sort of a fluid which is getting superheated. Then you can run a turbine with it, and so on and so forth. All right? NIF has not reached this stage yet. Okay.
How long does the one pellet that they do use last?
In 20 nanoseconds, it's gone. All right, it's finished. That's what I had wanted to show you, and I think I wait a minute. Target with fusion new text. I think this is the one. Sorry. Yeah, this is what I wanted to show you. Okay, so again, we got a deuterium nucleus and a tritium nucleus. All right? They're going to come together, high pressure and temperature, X-rays, helium nucleus, and a whole bunch of kinetic energy. Right? And all that kinetic energy in the form of neutrons could be used. It's energy. You convert it into, say, heat and run a turbine. Right? So that's conceptually what the NIF people want to do, to give us this inexhaustible source of energy that everybody wants. Okay. Oops, sorry.
We can go and visit the thing. I mean,
you need clearances. When we used to visit it, we had to get all kinds of clearances. I mean, eventually, once I come back, I could organize a trip because I know some people there from my old days who are interested students. It's a very exciting place. Okay. Now this is what's happening in the target. Somebody asked me a question, hey, what's going on in the target? So I'll show you what's happening in the target. All right. This is the target. Gold can. There's a hydrogen target in there. This is deuterium gas. Compression.
And then X-rays also would come out.
Yes, X-rays will come out. 20 nanoseconds, it's done. Now the laser could sit there idly, or what you could do is you could feed another pellet and repeat the process. So you have a continuous source of energy.
This energy remains stored there if you don't do anything.
If you don't use it, it's just going to overheat the thing. So that's why you have this fluid. Did you see in the previous one there was kind of a fluid going around which is absorbing all this energy?
And it can be used later on.
You just take the energy, heat water with it, and drive a turbine, and you continuously have, say, a power station, as an example.
How much heat comes out of it?
Megajoules per shot. Depends, actually. I'm sorry. The amount of energy we're putting in is megajoules. Depends upon the material. So basically, the way to look at it is that what happens on the sun is that if I take hydrogen and combine the two, and I get helium out, there is a net mass difference between the two. You lose mass. And that mass comes out as energy, equal to mc squared. How much comes out? I don't have a number on that. I'm sorry.
Yeah, there's a fusion energy.
It's fusion energy, yeah.
The energy that comes out more than the energy that was used to create the explosion.
Exactly. That's the whole idea of NIF. That the amount of energy it took to get that laser in there, the amount of energy coming out should be more than that in order for this to be useful.
And is it?
They haven't done it yet. They have not done ignition yet.
Oh, I thought.
But that's the hope. That is the hope eventually, once they perfect this machine, that the amount of energy coming out is more than the energy put in. Now we're talking about a source of energy, clean energy.
Basically the same way that we can make a fission bomb, we can also make a fusion bomb. It's so much energy.
But remember, a fusion material that we do is radioactive. There's no radioactivity.
Yeah.
Okay, that's why you want this, because there is no radioactivity here.